Okay then, so now it's time to talk about exponential objects. So exponential objects are really amazing. They basically allow us to sort of internalize the idea of sets of arrows into a category. So, I mean, one of the interesting things about category theory is that there's so many ways to refer to things. And an important idea is the idea of a set of arrows from A to B. Now, that's obviously the kind of thing that, on the surface looks like the kind of thing we talk about from a kind of external perspective. We stand there looking over the category and we say, oh, well, there are these arrows going from A to B, from object A to object B. But in many categories, particularly Cartesian closed categories, which I'll define, we have the property that there are objects which represent such collections of arrows. And these are exponential objects, and they're really important for lots of reasons. One reason is that they give this new perspective on arrows, and by relating them, we can prove lots of other things that don't seem like they're related to exponential objects. So they're sort of useful in a kind of existential sense. They're also very useful for making contact with things like computer science. Ideas like the lambda calculus of computer science can be sort of understood in terms of exponential objects. And basically, it sort of allows us to go from the particular to the general and understand this kind of relationship between the particular and the general in much more generality. Now, just to say something fuzzy, which may not be true, but it sort of might help to motivate the topic. Think about the real world. Think about someone who's an expert in how plants grow, in particular, how plants grow when different chemicals are applied to them. An agronomist or something. So let's say there's an expert in how plants grow when different chemicals are applied to them. Now, they're a person in the real world and they have this knowledge. So their knowledge is really about what kind of relationships there are between chemicals and plants. And so chemicals and plants are things in the world. Now, let's just fuzzily sort of pretend that the world is or say that maybe it is, but we'll say that the world is like a category. So we have the set of chemicals, A, and the set of plants, B. And now this guy is an expert in how chemicals interact with plant growth. So they're also in the world and they have this brain. And in this brain, they have all this knowledge about how chemicals interact with plant growth. So in a sense, they're a sort of internalization in the world of those relationships in the world. And that's kind of like what an exponential object is. It's something inside a category which represents the connections between one thing and another thing. Okay. Anyway, that's all very fuzzy. Let's get down to concrete mathematics. So what is an exponential object? Well, the exponential of b by a is an object which we write as b to the power of a with an arrow. The arrow is, the long name is e a comma b, but often I'll just write it as e. Okay, so we have this object b to the power of a with this arrow e, which goes from b to the power of a times a to b. So we're assuming we have products of pairs of objects, and it's this special arrow which goes from the product of this exponential object with a to b. Now, the way that you can think of this, just very fuzzily, if we're thinking in set, is that basically the elements in b to the power of a are functions from a to b. And so if we have a function from a to b paired with an element of a, what this E arrow does is it evaluates that function on a, which gives us a member of b. Okay, but anyway, that's just in sets. Exponential objects are much more rich than that in general. So let's carry on. We have this arrow E, but it has to have a special property. It has to have a property that for any arrow G, from any C times A to B, there's got to be a unique arrow G cup from C to B to the power of A, such that we have this equation holding E after G cup times 1 equals G. So this is the diagram, okay? This is really how we understand what an exponential object is. Given any G from C times A, there exists this unique G hat, which is called the transpose of G, and it has a G cup, I should say, and this G cup is called the transpose of Okay, let me back up. So the definition of an exponential object then, we have this arrow E, and it's such that for any arrow G from C times A to B, there exists this unique arrow G cap from C to the exponential object, which has this property that doing E after G cap times 1 equals G. So this is the diagram. This is really the way we understand exponential objects. We say that for any arrow G from C times A, there exists this unique arrow G cap, which makes this diagram commute, okay? And that's the definition of an exponential object. Now, I'm going to very shortly, I'm going to go into like the intuition behind this. It's important to have the intuition behind it, because it's a rather abstract concept, but just to say, so you can compare this with like previous things that we've understood, if you've internalized the ideas from the video on universal properties, I can say that this exponential object, which is b to the power of a paired with this evaluation arrow E, that's just really defined to be a terminal morphism from this functor which does the product with A to B. Okay, so I'm not going to elaborate on that too much, but if you watch the video on universal properties, that makes a lot of sense, okay? So anyway, just a few more definitions just to do some kind of bookkeeping, and then we're going to look at the intuition behind exponential objects. So this G cap here, this is called the transpose of G. And so notice that for any G from C times A to B, we have this unique transpose. And what that means is that for any arrow into our exponential object, for any arrow H, well, if we get that arrow H and then we compute Well, if we get the arrow h and then we compute e after h times 1, well, that's like sort of filling out this this part of the diagram. And so that'll define, and so that composition will give us an arrow, which we can call H cup. And H cup has the property that H is actually the transpose of H cup. Okay, so what I'm saying is that we really have these two different kind of arenas now that we can talk about arrows. And this is very important to understand. This is really the core idea behind exponential objects. Is it allows us to go from talking about arrows into the exponential object, so an arrow from c to b to the power of a, and we can go from that to get an arrow g from c times a to b by just taking this g cap here and doing e after g cap times 1. And conversely, if we have a g from c times a to b, we can convert that to get a g cap from c to b to the power of a just by using this kind of universal property, you know, that there exists this unique thing. So we can get it that way. So what I'm basically saying is that if we have an arrow h into an exponential object, we can always find a sort of arrow just from c times a to b, which this h is the transpose of. And we also call this h cup here the transpose of h. So we sort of use this word transpose to convert. So the transpose of this g is this g cup, and the transpose of this, sorry, the transpose of this g is this g cap, and the transpose of this g cap is this g. And when we're doing a transpose from an arrow from a product to an arrow into an exponential, we call the arrow into the exponential the cap of the arrow from the product. And conversely, when we have an arrow to an exponential and we convert it to an arrow from a product, we call the resulting arrow from the product h cup. Okay, so we have a property, of course, that h cup cap is h. Okay, so these cup and cap operations are just going either way between these two, and we have this equivalence. So when we draw this kind of vertical line, we mean that there's an isomorphism. So this is the sort of isomorphism which is involved with these exponential objects. I mean, it basically converts between them. So if we have an arrow g from c times a to b, then we can get this g cap, because this is a unique thing according to the definition of the exponential object, this unique arrow g cap from c to b to the power of a, with the property that it makes this diagram commute. And conversely, if we have an arrow from c to b to the power of a, then we can just call that g cap and use this diagram and, you know, take e after g cap times 1, and we get g. By the way, I'm using 1 here to denote the identity arrow. So I have been calling them ID, but I'm calling them 1 now. It's more sort of mathematical. And I will go over again what this notation of sort of doing the product of arrows means later, in case you've forgotten. Okay, so let's look at some examples then. So these are all really examples that could be viewed as happening in the category of sets. So this first one's a nice example. So, I mean, basically, we're talking about this correspondence here. And let's just take some examples. So what about if A and B are both real numbers and C here is this set of kind of, we could call them unitary operations, or, you know, functions from numbers, functions that take in a number and spit out a number, basically. So think about a calculator, for example. I mean, I know in calculators you have things like plus, which involve two inputs, but you also have these kind of buttons that just take one input and give one output, like square root, log, square, and so on. Okay, so think about sets. Sorry, think about C as the set of such operations, say on a calculator. So C is the set of these calculator buttons that just operate on a number and output a number. And A is the set of numbers. So what's an arrow G then from C times A? Well, you can think of it as sort of, once you picked a operation from C, you've really sort of fixed a certain kind of mapping, and then you can think about inputs from A, and you sort of do that. So maybe you pick an element of C to be, let's say, the square root, and then you can put in different inputs from A, and you get an output in B. Okay, so you can do square roots of different numbers, but that's just for a fixed kind of calculator button, square root. But if you have C as the set of lots of these, then what you really have is a sort of parameterization. So you can kind of like, every time you choose an element of C, you have a particular mapping from A to B. And that's really the sort of core idea of this relationship. So let's say you picked this element of C to be the square root, and you held that fixed, and then you varied your input real and kept evaluating this G here. So what you'd really be doing with that kind of fixed choice of an element of C is you'd be talking about a particular function from A to B, in particular the square root function. Okay, so that's really one of the kind of ideas. It allows you to go from this kind of idea of a parameterized mapping to something that actually sort of lifts the mappings out. I think it's actually maybe better to look at a sort of more graphical example. Well, okay, let's just see this for a start. Okay, so this is really a picture of what exponential objects look like in the category of sets, and I think this is really useful to get some intuition. So the basic idea is, like, we have this stuff in black. We've already talked about that. Now, let's suppose we start with some gamma comma alpha in C times A. Now, we can do G on that. So the output then would be G of gamma comma alpha. That's one way around. But what about going the other way around this triangle? This is supposed to commute. Okay, so what happens? Well, this, when we go along this arrow, like, what's this arrow do? Well, it's G cap times identity of A. So it keeps the alpha, it leaves the alpha alone, but it operates on the gamma by this G cap operation. Now, what's this GCAP operation do? Well, it takes in this gamma in C and it outputs something in b to the power of a. What is that? Basically, in the category of sets, that's going to be a function from a to b. So it takes this gamma and it outputs a function from a to b. Now, which function does it choose? Well, basically, it looks at the way that G operates when the particular gamma is held fixed, and that really gives us a function which sort of is like a function from a to b. It takes in an alpha and it outputs G of gamma comma alpha with that particular gamma fixed. So sort of more algebraically, what we'd say is that this function GCAP takes in this gamma and it outputs this function here. And what this function does is it operates on a sort of alpha dash, a member of A, and then it outputs G of gamma comma alpha dash. Okay. So this is really a function. This notation here means maps to. So what I'm saying here is that this is a function which maps a generic sort of alpha dash in A to G of gamma comma alpha dash. And another way we might write this, it might be a bit of an abusive notation, and I'm not really going to explain this too much, but if we know a bit about lambda calculus, we might write this as lambda alpha dash dot G gamma comma alpha dash. Okay. Now, what happens when we do this GCAP times identity here is that we replace this gamma with this kind of function here, which is sort of waiting for alpha inputs, and then it's going to do G using that input and using this sort of gamma, which it's now holding fixed because it got it from here. So we get that function, and then we also get alpha because the second part of this times IDA just takes the alpha from here and just leaves it alone and leaves it sort of paired with this function over here. And then the second part of this is this evaluation arrow. And all this does is it takes this function and then feeds in alpha as an input. And that gives us the same results. So I think a nice way to visualize this, I haven't seen this in any books, but I think it's a nice idea, is making a kind of visual way to think about this. So what's G? G is an arrow from C times A to B. So just for sort of understanding, let's imagine that A, B, and C are all numbers. They're all, let's say, real numbers. Okay, so then we can make this kind of 3D plot. So we put in an input which is like a gamma in C and some value of A, and then that's like a point in the plane, and then this surface here represents G, and how high a point is above a particular point on the surface represents the value of G gamma comma alpha. Okay, so that's fine. This surface is really representing G. But then how can we think about this stuff? Well, what happens? Let's say we pick a particular value of gamma, and we want to think about what's this mean? What's GCAP of gamma? Well, what GCAP of gamma is it gives us this function which takes in an alpha from A and outputs it takes in an alpha dash from A and it outputs G of alpha dash comma gamma. So what we can think of this really is the sort of slice of this surface sort of going away from us, because we've sort of picked a particular value of gamma, and then we've seen what kind of function from A to B we get by sort of just slicing through this surface. And so we can call this kind of blue curve, this slice here, G of gamma. And then if we evaluate this on a particular alpha, so we find the height of this curve for a particular alpha, like so, we'll get the same value as G of alpha comma gamma. And that's what this diagram says. Okay, but exponential objects are really, really cool. They're useful for much more than just sort of doing things with numbers. I mean, even staying in this arena of the category of sets, or sort of thinking about real world things, real world sets of interest, we can see there's many important usages. So for example, let's let this A, B, and C here be time, temperature, and space. Okay, so then we can think of G as a mapping from space and time to temperature. That makes sense, doesn't it? I mean, if you have a point in space at a particular time, that'll have a particular temperature. So suppose G gives us that. Now, what's this equivalent kind of transpose idea? Well, it'll take a point in space and associate that with a kind of map from time to temperature. Okay. So associating each point in space with a sort of log of what temperature it has at different times is equivalent to sort of saying what the temperature is at these different points in space-time. Okay. Another one is we can let A, B, and C be space, time, and particles. Okay, so if we take we can think of G now, it takes a particular particle and a particular time, and it gives us the position of that particle in space. Now, the sort of equivalent idea, this kind of transpose G cap, it takes a particle and it gives us the kind of trajectory of that particle, the kind of map from time to space involved in that particle. So again, associating each particle with a trajectory, which is what G cap does, is equivalent to associating each particle at each time with a position. So this is actually the really deep one, I think, because we can really relate this so well to, what's going on in the real world. There's other ones we can do, like situation, goal, and person. I mean, this is a little bit maybe inexact because there's obviously other variables, but we could say that if we have a person, then they have an idea what they'll do in different situations, what goal they'll have in different situations. So we can think of their kind of personality as defining some kind of map where it takes in a sort of situation and outputs a goal. And the kind of equivalent notion then is that we have this way of associating a person in a situation with a goal. Okay. And then there's similar ones, data, A, B, and C, a data, conclusion, and an observer. That's kind of similar to the last case. Another one, resource, allocatee, and environment. So if you have some kind of resource allocation scheme, you might say, well, given a resource, there's a kind of, maybe that corresponds to a kind of function that given a resource and an environment, we want some kind of function which picks out particular allocatees to get that resource. And that would be equivalent to this kind of map here. Which takes a particular environment and gives us a map from the resources to the allocatees, the people who might get those resources. Okay, so there are a few sort of real world connections. Now let's make sure we understand the terminology properly. So, I mean, I think this is a fundamental thing here, really. Categorical product, of course, we have to understand. So just to very quickly recap, categorical product of A and B is A times B with projection arrows P1 and P2, such that for any arrow C with an arrow F to A and an arrow G to B, there exists a unique arrow which we call angle brackets F comma G, and that goes from C to A times B, and it has a property that P1 after F comma G is F, and P2 after F comma G is G. So I've said there exists this unique arrow which makes this diagram commute. Of course, there can be more than one arrow from C to A times B, but there's only supposed to be one which makes this black diagram commute, okay, for any particular F and G from any C. Okay, so the core kind of formula that I want to get is this one. That if we have another arrow X from D to C, then we have the F comma G after X equals Fx comma Gx. When I say stuff like Gx, I mean G after X. I'm not writing these circles today. So this is a core formula. I'll leave it to you to think about the proof of it, but it's extremely useful. I mean, basically, the idea is that, you know, we can compose this X here with this black intermediary arrow, and that gives us this bigger intermediary arrow, which is the intermediary arrow for these purple arrows, Fx and Gx, okay? So this is really fundamental, this formula, and it allows us to understand, well, we can use that kind of notation again to understand what the product of arrows is. So let's say we have an arrow F from A to A dash and an arrow G from B to B dash. Then the arrow F times G is this arrow from A times B to A dash times B dash, and we can just really define it to be F after P1 comma G after P2. So I mean, the sort of idea is that, you know, if you compose these arrows like F after P1 and G after P2, then you can think of A times B as a kind of candidate for being a product of A dash times B dash. And then this purple arrow is the unique intermediary arrow. Okay, so that's the technicalities. Now, why are we calling this thing an exponential object? Like, why are we calling it? Why have we called it b to the power of a? Why in set does it correspond to the set of functions from a to b? Well, it's really because of this kind of relationship here. So, in order to understand this, we need to understand that a is isomorphic to 1 times a, where 1 is the terminal object. Okay, so let's just make sure we understand that. So how do we construct an isomorphism between these things? Well, the important thing to realize, really, the core of matter, I mean, we write exclamation mark a to denote the unique arrow from a to the terminal object. And let's say we want to work out the product of 1 and a. Well, of course, we can just write this normal kind of notation, 1 times a with projections p1 and p2. But also, we could also write the product just as a. And if you have, for these projection arrows, you have exclamation mark a and the identity of a, you can really check that that works just like a product should. It has the right properties. But let's be a bit more direct about this. Let's actually cook up the isomorphisms between 1 times a and a. So they're isomorphic because they're both products of 1 and a. So let's actually suppose we have this product here. So we have 1 times a and we have some product of it involving P1, projections P1 and P2. Now we already know right off the bat that P1 has to be exclamation mark 1 times a, because 1 is a terminal object. There's only one arrow from 1 times a to 1. And as I say, we denote these arrows to the terminal object as an exclamation mark. Okay. So here we have the product, and we can think of a as a candidate here. So this candidate A has these arrows, exclamation mark A and identity A. And so it has this unique intermediary arrow in purple here, which we can call exclamation mark A, comma 1A. And that's going to be an isomorphism, actually, is that arrow. So we may write this as we might write it like that, okay? So this is just putting this squiggly line underneath our arrow to note that it's an isomorphism, okay? Now, how can we see this as an isomorphism? This is important. So, well, we need an inverse, and I claim that the inverse of this is just P2, okay? So how can we see this? Well, it's quite easy to see that P2 of exclamation mark A, comma 1A is 1A, because all P2, when we do P2 on this, we're just going to be selecting the second entry from this pair, so we get 1A from that. But we want to do the converse as well, so to prove that we have this sort of pair of isomorphisms, we also have to show that this purple arrow after this orange arrow gives the identity on 1 times A. So let's call that composition X. We want to show that X is the identity. So how are we going to do it? Well, x here is exclamation mark a, comma 1a after p2. And using that formula I was just talking about, we can take this p2 inside the brackets. So we can rewrite this as exclamation mark 1 times a, comma p2, because when we compose p2 before 1a, we just get p2. And when we compose p2 before this arrow to the terminal object, we just get another arrow to the terminal object, but this time it comes from 1 times a. So we have this. So all we want to do now is we want to show that x here acts just like the identity. Because if we just think about the outside of this diagram, there can only be one arrow from 1 times a to 1 times a, which makes it commute in the sense that, so one arrow x in that such that p1x is p1 and p2x is p2. And that has to just be the identity of 1 times a. So if we can show that p1x is p1 and p2x is p2, then it follows from the uniqueness of an intermediary arrow from the product of, from this product to itself, it follows that x has to be the identity arrow. Okay, so to see that p2 x is p2 is easy because p2 just selects this second entry, which is p2, and show that p1x, well, we have that that's exclamation mark 1 times a, but that's just p1, that's what we defined it as. So x we can just write as p1 comma p1, or we can just write it as the identity of 1 times a, because it's this unique intermediary arrow, and we know that using the identity of 1 times a in place of this x has just these same properties, and there's only one such arrow with these properties. So there we go. Okay, so we've got that. So we have this a here is isomorphic to 1 times a. And now we can really see why, you know, this identity, sorry, we can really see why this exponential object is referred to often as this kind of object representing the maps from A to B. And that's because if we have a general kind of arrow from A to B, by what I just said, that's equivalent to an arrow from 1 times a to b, and then using our kind of taking the transpose of this, we get this unique arrow from 1 to b to the power of a. So in other words, a point of b to the power of a, as in an arrow from the terminal object, corresponds to an arrow from a to b, and vice versa. So, I mean, this is a big deal in the category of sets, because an arrow from the terminal object into an object in the category of sets just picks out an element. So when we're working in the category of sets, b to the power of a really is the set of functions from a to b. It's kind of elements, each element in it corresponds to a function from a to b. Now, more generally, let's say we're working in the category of graphs or something like that. I mean, in a graph, for example, there are a point in a graph. Well, the terminal object in the category of graphs is just this single vertex with a self loop. And so a point in a graph is just going to be a self loop. But of course, not all graphs have them. So there are some graphs that don't have any points at all. They don't have any arrows into them from a terminal object. But the exponential graph, sort of taking one graph to the power of another, that does have points in it that represent, and each of those corresponds to a graph homomorphism from graph A to graph B. But the exponential graph, b to the power of a, has more structure than that. And that's because really an exponential object does more than just sort of collect together these maps from A to B. It also has this property that it can kind of emulate these parameterized maps. Okay. Anyway, let's sort of go through the formalities of how we can talk about how b to the power of a really sort of collects together these different maps or morphisms, I suppose, or arrows from A to B. So let's suppose in a general category, well, a category of exponential objects, products, terminal objects. Let's say we have an arrow f from A to B. So given such an arrow, we can find the sort of name of it. And that's just going to be the transpose of f after this kind of, that's going to be the, well, if we get f, and when we do f after this isomorphism from 1 times a to a, so this is so this is P2 here. So if we get f after P2, that'll be an arrow from 1 times a to b. And then if we take the transpose of that, then we get this arrow from 1 to b to the power of a. And we call that the name of f, okay? So we often sort of write it with these quotes here. So that's a point of the exponential object, which really sort of represents this arrow f from A to B. I mean, it technically, that's because we have that so that's how we can sort of go from an arrow to a sort of point of our exponential objects. Now we can, conversely, what we can do is we can go from, let's say we just have a point of our exponential object. So what we can do then is we can form this kind of arrow here. So here, this is the other isomorphism between a and 1 times a. So this is exclamation mark A, comma 1A. So if we take this x cup here, which we could write as E after x times 1A. Okay, if we take this x cup here, let's say this x, this is the name of it's a point of the exponential object, but we say it's going to be the name of an arrow from A to B. So what is that arrow from A to B that it's the name of? Well, if we take x and then we do the transpose of it, so we change it into an arrow from 1 times A to B, that's x cup. And I mean, really, x cup is E after x times 1A. Well, if we do that arrow, after this arrow, which converts us from an A to a 1 times A, this is our isomorphism, exclamation mark 8, 1A. So if we do x cup after exclamation mark A, 1A, well, that'll give us the arrow which this point x here is the name of. Okay, so you can check this yourself. But basically, this is how we go backwards and forwards between sort of general arrows in our category from A to B and points of the terminal object, b to the power of A. Now, I mean, that's kind of interesting in itself, but more interesting is we can actually compose arrows. We can compose them kind of internally, so sort of inside the exponential objects. I mean, we can really think of this arrow x from 1 to b to the power of A, if we like. We can think of it as something sort of inside the exponential objects. And we can really think about arrow composition as happening inside as well. So, I mean, very roughly, if you think about this exponential object as a sort of repository of knowledge about relations from A to B, you can think of this kind of internal composition as something like, something inside the category, kind of like thinking or something. But anyway, that's a bit fuzzy. Let's the kind of, so I'm going to introduce this idea using this notion. So I want to basically introduce this idea of how we can sort of think about arrow composition kind of internally. So I want to introduce this idea about how we can sort of think about arrow composition as happening internally in exponential objects, but more concretely, what I really want to do is to show that, like, when we have all the products in our category and we have these exponential objects, we really have a functor. Okay, so there's really a sort of exponentiation functor, and more concretely, this is really the right adjoint to our product functor. Okay, so this will make sense if you followed my video on adjoint functors. If you haven't, then don't worry, because we're not really going to rely on adjoint functors too much. It's just maybe for the next 10 minutes, I'm going to show how we can get the concept we're after, how we can see it emerge from the theory of adjoint functors. But this is just really about introducing a concept And once we've introduced it, we'll sort of have a definition of it, and we don't really need to see exactly where it comes from. So if you're not into adjoint functors, you can block your ears up without losing anything. But anyway, so we have the category C, and we also have another copy of the category C, let's say. Now, we can think of there being a functor, this kind of product by a functor. It goes from C to C, and it takes an object and it outputs the categorical product of that with A. And it takes an arrow and it outputs the categorical product of it with the identity of A. Okay. So this is our sort of product functor. And then the right adjoint to that is going to be this functor here. And that's actually our exponentiation functor. Okay. So the way this basically works is, let's say we have an object B and we want to do this kind of exponentiation functor on it. So what we can say is that the output of that is well, if we get a terminal morphism, terminal morphisms are unique up to isomorphism. So if we get a terminal morphism from blank times A, this functor here, to B, well, that's going to consist of an object over here on the right. We can call that object B to the power of A, together with an arrow from where that object got sent under blank times A to B. Okay, and that's this evaluation arrow. This arrow E from B to the power of A times A to B. And that has a property, because it's a terminal morphism, I mean, it's really defined by the property that for any object C over here on the right, if we do this blank times A functor on it, we get C times A, and if there happens to be an arrow G from C times A to B, then there has to be this unique kind of intermediary arrow, which we call G cap, which has the property that when we lift it under blank times A, so we get G cap times 1A, and we get the E after that is G. Okay, so that's really the sort of nature of exponential objects in terms of sort of talking about them as terminal morphisms. Now, the way this works when we're talking about adjoint functors, say we want to construct the right adjoint to blank times A. So we want to get the right adjoint of this. Well, the way we do it for any B, we take this terminal morphism from blank times A to B, and then that terminal morphism consists of an object and an arrow over here on the left, and the object is the thing we want, B to the power of A, and so we define that as the output of doing this exponential functor, this right adjoint on B. So blank to the power of A operating on B gives us B to the power of A. And also it defines this evaluation arrow E here, which goes from B to the power of A times A to B. This is really the arrow involved in this terminal morphism. Okay. So that's fine, but we kind of knew all that already because we already absorbed the definition of a term of a exponential object. But what we really want to know now is, okay, if this is a functor, how does it operate on arrows? And this is interesting. So, okay, we have this then, that the exponential functor, sort of blank to the power of a, is the right adjoint of this product functor blank times a, which is interesting. But yeah, we want to know how this thing works on arrows now. So we can really get this by using the kind of theory of adjoint functors, like so. So this is the construction. It's a specific example of this kind of adjoint functors construction. I think I talk about it about 45 minutes through my video on adjoint functors. But the basic idea is like this. We have this arrow f from B to C, and we want to construct an arrow which we could call f to the power of a, the kind of exponentiation of f. Okay. So how are we going to do this? Well, what we're going to do is we will work out the what this exponentiation does on B and what it does on C. In other words, we'll get a terminal morphism from blank times A to B, and that'll give us B to the power of A, and this evaluation arrow here from B to the power of A times A to B. And we'll do similar with C. Okay, so we get this stuff. And then we have all these black arrows here. And then if we just compose F after this EAB evaluation arrow, we get F after EAB. And now we can think of that as a kind of candidate arrow for going into C. So we have this sort of true terminal morphism here involving this black arrow, E, A, comma, C. But what we also have here is we have, oh, look, there's this object B to the power of A over here, and where it gets sent under blank times A, there's an arrow from there to C. Okay, so that means by the definition of this black stuff at the top being a terminal morphism, that there has to exist this unique kind of intermediary arrow like this, which if we lift it under blank times A, then it makes this diagram commute and allows us to emulate the effect of the purple arrow. Okay, this is the basic idea with adjoint functors. So the long shot of it is that then there exists this unique arrow from B to the power of A to C, which is unique with the property that, with respect to the property that it makes this diagram commute. Okay, so we have that, well, I mean, we can call this arrow, we could call it, using our previous notation, we could call it the transpose of this purple arrow. So we could call it the transpose of E, A, comma, B. That's its sort of proper name, following this kind of convention here. But alternatively, we could just call it F to the power of A. And it's this unique arrow with the property that f to the power of a times 1a makes this diagram commute. Okay, so we have f after EAB is EAC after f to the power of a times 1a, where f to the power of a is the transpose of f EAB.